Let's go ahead and get started. We've got another really interesting method to learn today. Today's class, though, we won't be doing an iteration with Excel, so it's not as exciting as the three reservoirs approach was, but still the nodal method is today the prelude to big things to come, so I'm excited to share it with you. Let's see, you've got an assignment due on Wednesday. Both of those problems have to do with the three reservoirs problem that we set up last time, so if you have any questions on that, please feel free to stop by during my office hours. I'm happy to help you with it. Just to remember what we did last time, we had this situation where three reservoirs were connected in a common junction, and the uncertainty arose from what the flow rates would be in each of the pipes, and then for the pipe going to the middle reservoir, what direction the flow would be. And so what we did was since we don't know exactly how much energy there is at D, we just assumed something, and we had to come up with some corresponding friction factor and velocity based on that assumption, and then we iterated back and forth by checking the continuity expression. What is the flow in versus the flow out at D? And we knew that our solution had converged when two criteria was met. One was that the flow rate in equaled the flow rate out, and the other was that within each step, the F values weren't changing any longer, or that the change was extremely minor, that we had converged on both an F value and on flow rate in being flow rate out. So any questions about that general approach before we move on? I don't remember what that was supposed to be. So. All right. Well, just to kick things off last time, what we did was we took a look at the flat range on the Moody diagram, and we said, for our first guess of F, we would assume that the F value was independent of velocity. So in other words, the F value is in this range where we have an F value that depends only on the ratio of the equivalent roughness to the pipe diameter. So in other words, the relative roughness ratio. This is the Jane equation. And when we're making that assumption that we're in the fully turbulent range, the Jane equation simplifies because the effect of the Reynolds number term, it's so big that that part of the expression goes away completely, and all we're left with is that the F value is a function of K sub S to D. So if we say, let's assume it's fully turbulent flow, that's a way of very directly and easily calculating the F value a first time around. So we wouldn't necessarily have to go to the graph like we did, but you could calculate the F value by the relative roughness and what's left of the Jane equation once you ignore Reynolds number. The same thing is true of the Colebrook equation, that what was once an impenetrable iterative equation that is implicit becomes less implicit. Actually, it becomes explicit because the Reynolds number is so big that this whole term cancels out, and all that we're left with is the effect of the relative roughness in calculating F value. So if we just write on our paper, assume fully turbulent flow, during our first iteration, we can calculate our first guess value of F very easily. And then once we have the guess value of F, we can use it to calculate the actual velocity and then see if that was a good assumption. We would always need to check to see if it's fully turbulent flow like we thought it was. And how do you know if it's fully turbulent flow? Well, you would calculate a new updated F value based on the full version of the Jane equation or the Colebrook equation. And if the F value was the same when you did account for the Reynolds number as when you didn't account for the Reynolds number, then it's fully turbulent. The Reynolds number is big enough to become insignificant. We're going to use that assumption when we kick off the process to solve the multiple pipelines problem. The basic principle we're going to use in this new nodal method is considering flow balance, which is one of the same tools that we used in the 3 reservoirs problem. That is when 2 streams go together at a junction, the sum of their flow rates is what goes out. In this diagram, Qx plus Qy equals Qz. So continuity expression. And we solve it by considering what happens inside of some control volume. Flow goes in, flow goes out, and in the case of an enclosed junction, there's no accumulation. Here's where we're going to be applying it. Flow going through a pipe at a known flow rate, and then reaching a junction where it could go partially through the top pipeline, partially through the bottom pipeline, and we don't know necessarily what the relative flow rates through each are. But we know that when that pipeline joins together again, if there haven't been any pipes like sideline laterals taking water off, if it's still fully enclosed and there's no reservoirs that are allowing for accumulation or depletion, no storage opportunities, then the flow rate, once they come back together, is that same known flow rate as went into the junction. So how much will go through the upper and the lower pipes is sort of what we're after. And the application of this continuity expression is sort of hinted at the bottom of the screen there. We know that the flow rate through the top pipe, pipe B, is the initial flow rate through pipe A minus how much was going through C. Or we can say and the flow rate through the lower pipe is just what was the flow rate A minus however much is going through the top. We're going to substitute one of these expressions into a relationship that relates the two so that we can solve directly for both of them. And before I show you that equation, let's just think about it in qualitative terms. How much flow will go through the top pipe versus the bottom pipe? And we'll get sort of a general sense for how the system behaves before we start plugging numbers into equations. So let's just say, for instance, that the pipe lengths are the same. That pipe B and pipe C have the same length, the same diameter, and they're made out of the same material, meaning that their roughness is the same. So how would the flows be compared? They're equal. There's no reason why there would be more flow rate going through B than C. There's the same resistance to both, same resistance to flow in both channels, and so the water would go equally through both of them. Okay, let's say in the second example, what if they both have the same diameter and the same pipe length, but pipe B, which is the top one, is more rough? So which would have more flow? Pipe B or pipe C? C is going to have more because B has more roughness. There'd be more resistance. So water goes the path of least resistance. More of it will go through pipe C. There will still be some that goes through pipe B. It's not that there will be no flow rate. Just making a slightly rougher pipe doesn't cut off all the flow together. We'd have to put in some sort of a valve or a gate, a blockage of some sort to have zero flow rate. But relatively speaking, there'd be more going through the smoother pipe. What if the diameter of pipe C is bigger and everything else is the same? How would the flows compare then?
More in C.
More in C. Why?
There's less friction loss in the larger pipe.
Okay. Larger pipe means slower velocities. Slower velocities means less friction loss. Less friction loss is the reflection of the fact that there is less resistance to flow. And so more is going to go through the pipe that gives it less resistance. More students go through classes that offer the least resistance, right? Water students, we all seek the path of lower energy. Well, not always, because you're in engineering. You could have majored in communications or childhood development or something. But business management. Is that the easy one on campus here?
It's like half of our arts classes.
Yeah.
Criminal justice.
Criminal justice. Let's make fun of other majors. For the record. All right. Okay, now what about if pipe B has a bigger diameter than C, but it's longer. We haven't talked about pipe length yet. A longer pipe is going to have more resistance, right? So pipe B has a bigger diameter, which would mean less resistance, but now it's got a longer pipe, which means more resistance. C is more rough than B. So what are the flow rates going to be here? It's inconclusive. We don't know just based on the information that's given there. We're going to have to find maybe the relative contribution of each. Like, which is more important? Is it more important that the length of B is longer or that it's smoother? Because those could potentially cancel each other out, but that's unlikely that that the effect of each would be exactly equal. And so there has to be some way for us to account for all of these variables at once. And what we know, what allows us to account for that, is that regardless of the flow path, the energy loss through B and C are going to be equal. And the reason why is that the water is going from one junction to the other. And it's going to have some amount of energy at this first junction. It's going to have less energy at the second junction. But it doesn't matter if you go through the top or the bottom, the energy loss is going to be the same. If the energy losses weren't the same, then that would mean that we had like a contradiction. It would mean that at a point there were two different energy levels. And that can't be true. If you've got a known amount of energy at this junction, then you're going to have the same amount of energy downstream regardless of whether you went through the top pipe or the bottom pipe. And so here's the expression that allows us to equate the relative importance of friction factor, pipe length, velocity, diameter. And so does this expression ring a bell for anyone? Does that look familiar? What is this expression down here? It should look familiar. We've been using it a little bit lately. It's the formula for head loss. What do we call that formula? It's the Darcy-Weisbach equation. So we're saying that if the head loss through each of the pipes is equal, then the formula for head loss, FLV squared divided by D2G, the Darcy-Weisbach equation, that you can go through either one of the conduits, and the energy loss is because of those components that contribute to energy loss, and so it's equal. What we're going to do is substitute all the known information that we have for the Darcy-Weisbach equation into the Darcy-Weisbach equation, and then apply these relationships, where the flow rate and therefore the velocities are going to be related in terms of each other. That's the direction we're headed in this nodal method. So it doesn't matter how you get from location 1 to location 2. You go through the top pipe or the bottom pipe, the head loss between the 2 points is the same regardless of the route. And that seems a little bit, it's an intellectual jump at first when you think that, oh, how is it? Is it coincidence that there's the same energy loss through both of them? But that's just a reflection of equilibrium. If for a very brief moment the head loss wasn't equal through the top and the bottom pipe, then all of a sudden more water would go through the conduit that had less head loss until they were equal again. And so that imbalance can't exist for more than just a fraction of a second before more water would flow into the preferential channel and then they're equal again. So we're going to apply this process, and this is a new equation. Well, it's a new format of an old equation. This is actually just the energy equation. And so let me write the energy equation on the board, and you can see if you recognize the difference between this and the old form of the energy equation that we usually see. Z1 plus P1 divided by gamma plus V1 squared divided by 2G plus HP is equal to Z2 plus P2 divided by gamma plus V2 squared divided by 2G plus FLV squared divided by D2G. All right, so what's the relationship between the energy equation that I've written on the board and what we're looking at here on the screen right now. Well, first of all, for H, what they mean by H is all these normal terms of the energy equation. So Z1 plus P1 divided by gamma plus V1 squared divided by 2G. So the elevation, pressure, and velocity head, add all that together, and I'm going to call it H1. All of this for 2, the elevation, pressure, and velocity head, that's H2. So what we've got is H1 plus HP is equal to H2 plus FLV squared divided by D2G. So we're getting closer. We're getting closer. Oh, also there's a term here for local losses. So this is the friction loss term, H sub F. There's also a local loss term, KV squared divided by 2G. Okay. So some other little differences. The friction loss equation, instead of being expressed in terms of velocity squared, remember I told you in a previous lecture that sometimes we'll express it in terms of Q squared divided by A squared, because it'll be more convenient. This is one of those occasions where it's more convenient. And so instead of saying V squared, we're going to say Q times the absolute value of Q, that's essentially Q squared, divided by A squared. All right, so that's one transformation. And over here, you can see there's something going on with the pump term. So instead of just plain old HP, what I'm doing is Q divided by the absolute value of Q. Now the purpose of that, if you divide Q divided by Q, it does nothing, except for that if the flow direction will result in a positive or a negative term, then what you've just done in this expression is you've built in some sort of a way to indicate if water is really going from 2 to 1 instead of 1 to 2. In this equation, what it assumes is that water is flowing from junction 1 towards junction 2. And so the purpose of these absolute values in the flow rate terms that you see, instead of just saying Q squared, for example, here, they very intentionally had one of the terms be absolute value of Q and the other one isn't, so that if the flow direction is negative, that you retain that negative sign overall. All right, so I think that you can see that if you have H2 minus H2, and then take everything else over to the other side of the equation, that the local loss term is K Q times absolute value of Q divided by 2G A squared. We can combine many of the components of these, and you see that the Q times the absolute value of Q divided by 2G A squared, that's common between both the friction loss term and the local loss term. And so they've combined the things that are in common. Here in parentheses are those things which aren't. Either they're the individual components of the friction loss and the local loss terms. So this is the process that we're going to be applying to solve the nodal method, and all of the variables are defined there along with their units, nothing that we haven't seen before, except for I want to emphasize that location 1 is upstream, meaning where water is coming from, and location 2 is downstream, meaning where the water is going to. And the reason why that convention has to be applied is that the pump head is to be added to the left-hand side of the energy equation, and the losses are added to the right side of the energy equation. Because between 1 and 2, energy is added by a pump and taken out by losses due to pipe friction and local losses.
What area would you use on that?
It's the cross-sectional area of the pipe.
Okay. before and after the split?
Through the conduit. And so if they're different pipe diameters, you use this equation through one of the conduits. So you're saying, I want to find the head at 2 in terms of the head at 1 through the top pipe. Then you'd apply the area, the flow rate through the top pipe. We're talking about all of the things through that top pathway. So I'm glad you asked that question, because we're just applying it through one of the 2 routes that water could be going through. Actually, we'll apply it to both, because the head at 2 is going to equal the head at 2 regardless of whether you go to the top or the bottom. So we're going to set this equation equal to itself. One on the left-hand side, one on the right-hand side. That's the problem-solving process we're going to be going through today in this example. We'll find all of the energy at 1. We'll find the total head there, meaning the elevation, pressure, and velocity head. And then we're going to find the head at 2 in terms of the top route. Also write an equation for the head at 2 in terms of the bottom route. And remember that QB and QC aren't known. So not only do we not know how much head there is at 2, but we don't know what the flow rates are. But we do know that the head at 2 is equal to the head at 2, regardless of whether you go to the top or the bottom. So we're going to write this equation that's at the top of the screen there twice. Once in terms of the top route, once in terms of the bottom route, and then we're going to set them equal to each other. All right, so here we're applying the nodal method. And in this example, we've got a location A, where we know the pressure at this location A. We know its elevation, we know the flow rate, and we know the pipe diameter, so we can find the velocity head at A. So those are the 3 terms that we would need to know how to find the total amount of energy at A. We can find the energy at B by applying this formula. We would just apply the energy equation to find how much losses are there between A and B. We've got some new elevation we're going to have to take into a consideration. We know that through pipe 1 there's a certain length. It's got a certain area, velocity, relative roughness, F value. So that all the terms we would need to find how much energy loss there is between A and B. So it's not really anything special or indeterminate going between A or B, but it is a little bit more challenging when we want to find the pressure at C, because once we go to find the pressure at C is when we're going to have to relate the flow through the top channel to the flow through the bottom channel. All right, so what I'd like you to do is apply this process, but I'm going to just give you the shortcut sort of head start that if you want, all you want to do is find the relative flow rate of 2 versus 3. It's actually simpler than starting all the way at A. You don't have to find the total head at A, then find how much losses there are at B. You can start off just by applying F2, L2, B2 squared divided by D2, 2G is equal to F3, L3, B3 squared divided by D3, 2G. All right. So here's what you need to do. First of all, assume fully turbulent flow. Once you've assumed fully turbulent flow, then that allows you to find F2 and F3. Once you know F2 and F3, then you can set in all of the other information you know about the relative lengths, the diameters, and so forth. and then find the velocities in terms of each other. So I'd like you to answer the question, what is the flow rate at 2 and what is the flow rate through 3 using the fully turbulent flow assumption and substituting into this friction loss equivalence. So in this example problem, what we first did was applied the fully turbulent flow assumption and found F2 is 0.0149, F3 0.0157. And then we set these two expressions equal to each other and solve for V2. We could have also written it in terms of V3. Either one would work. It doesn't matter which. In this case, solving for it in terms of V2, canceling out the 2G that's in both the numerator and the denominator, substitute in all the known values for the diameter, friction loss parameter, the pipe length, and then we get the velocity at 2 in terms of the velocity at 3. And once we have that known, we can substitute that into the overall continuity equation. The overall continuity equation tells us that A2V2 plus A3V3 is equal to the 3 cubic meters per second that's going through the entire system. And so substituting in, instead of V2, what we know is that the velocity through 3 is faster than the velocity through 2. We substitute in that expression in terms of V3, and that becomes the only unknown in the continuity equation. We can find the velocity through pipe 3. Once that's known, we can find the velocity through pipe 2, and then the flow rates through each of them, since the cross-sectional areas are known. And just to check to see if everything works out, we add the two flow rates together and find that it's 3.001 cubic meters per second. So that minor difference is just on account of round-off error. So now that we know the relative flow rates through each, then we could find the head at B, we could find the head at C, the head at D. Everything else falls into place really easily. Really, the only new information here in the nodal method is just to consider what's happening at each of the junctions and the realization that the head loss is the same through pipe 2 as it is through pipe 3. That we have to have an equal amount of head loss in order to solve this method. And so let's double check that. Let's see if that ends up being the case, that we have the same head loss through each of the pipes. So head loss through pipe 2, FLB squared divided by D2G. Okay, so the F for pipe 2 that we said, 0.0149. Pipe length is 500 meters. The velocity through 2 is 9.98 meters per second. The diameter through pipe 2 is 500 millimeters, so 0.5 meters. 2 times 9.81 meters per second squared. And the head loss through pipe 3 is going to be 0.0157. The length of pipe 3 is 550 meters. The velocity was 8.27 meters per second squared divided by the diameter, 0.4 meters, and 2G. All right, let's all do that together. I don't have those values solved.
the 3.
Huh?
I got that for
You got
3
the
as
same?
well.
Good.
If you only go 1 decimal, if you go to 3, it's a little bit.
Okay, so it looks like the head loss is the same regardless of route. What was the other assumption that all of this hinged on so far? Yeah, we invoked the fully turbulent flow assumption, 75.6. We invoked the fully turbulent flow assumption, and so what we need to do is, now that we've got this velocity, find the Reynolds number, and with the Reynolds number, go back to the full version of the Jane equation to make sure that that's valid. We don't have the time to do that check, but that is a check that I would like you to include on a quiz or an exam or a homework problem where you invoke the fully turbulent flow assumption. It's a very helpful tool, but you have to make sure that it's valid. And if not, then your reaction is to redo everything with your new and improved F value. So you hope that the fully turbulent flow assumption ends up being valid or that you're using Excel.